Most breaches don't start with an exotic 0-day. They start with a permission check nobody wrote, a default password nobody changed, a library nobody looked inside. OWASP, the open project that publishes the industry's reference list of application security risks, keeps counting them, and the same 10 categories keep coming back. Here is the current list, all 10 start to finish. For each one, what it actually is, how an attacker exploits it, and what a real defense looks like. Enough that you can name it in a design review or in an interview without blinking. So which one sits at number 1? That's where we start. Let's kick off the OWASP Top 10 for 2025 with the risk that tops the list: broken access control. Access control is simply the rulebook that decides who's allowed to do what inside an application, which pages you can see, which records you can touch, which buttons you're allowed to click. Think of it as a gatekeeper standing between a user and the data behind the wall. When that gatekeeper is built correctly, a regular user tries the door, gets checked against the rules, and either gets waved through or turned away. Broken access control means that gatekeeper has a hole in it somewhere. Maybe a check that was forgotten on one page, or a rule that only lives in the front end and never gets enforced on the server. Attackers love this category because it's usually not flashy. There's no clever exploit code, just changing a URL or a request parameter and watching the server hand over something it shouldn't. That's exactly why it's been the number 1 risk on the OWASP list. It's common, it's easy to find, and the damage can be enormous, from viewing someone else's invoice to taking over an entire admin panel. Before we go further, let's separate two words people mix up constantly: authentication and authorization. Authentication is proving who you are. You type a username and password or scan a fingerprint, and the system confirms your identity. Authorization is a completely different question. Now that we know who you are, what are you actually allowed to do? You can be perfectly authenticated, a real logged-in verified user, and still be authorized for almost nothing outside your own account. Broken access control lives entirely in that second box. It's not about fake logins or stolen passwords. It's about a system that correctly knows who you are, but fails to correctly check what you're allowed to touch. A classic mistake is developers checking authorization once on the login screen and then assuming every request afterward is automatically safe. In reality, every single action, viewing a record, editing a file, calling an API, needs its own authorization check every single time on the server. Skip that discipline anywhere in the app, and you've created a gap an attacker can walk straight through. The single most common flavor of broken access control is something called an insecure direct object reference, or IDOR for short. Here's the coffee table version. Imagine your invoice lives at a web address ending in /invoice/1042. You're logged in, you view your own invoice, everything's fine. Now you simply change that number to 1041. If the server trusts that number blindly, pulls up whatever record matches it without checking that it actually belongs to you, congratulations, you're now looking at a stranger's invoice. That's an IDOR. The object is being referenced directly by an ID the user controls, and nobody on the server side ever asked, does this ID actually belong to this user? It sounds almost too simple to be real, but IDOR bugs are found constantly in production apps because it's easy for a developer to write the query that fetches the record and forget to add the ownership check. The fix is conceptually simple too. Every time you fetch something by ID, verify the logged in user actually owns or is permitted to see that specific ID. Next flavor, missing function level access control, sometimes called vertical privilege escalation. This is less about which record you can see and more about which features you can use. Picture an application with two kinds of users, regular customers and administrators who get an admin panel for managing accounts, refunds, or system settings. The intent is obvious. Only admins should reach that panel. But if the only thing hiding that panel is a button that doesn't render on a regular user screen, that's not real protection. The admin page itself might still be sitting at a perfectly guessable web address, and if the server doesn't independently check, is this specific user actually an admin before running that page's logic, a regular user can simply type the address directly and walk right in. This is called vertical escalation because the user is climbing upward from a low privilege role to a high privilege one without ever actually earning that privilege. It's a favorite in real breaches because admin functionality is high value. User management, financial controls, configuration, exactly the kind of thing you don't want exposed by a missing server-side check. There's a sideways version of this problem too, called horizontal privilege escalation. Instead of a low privilege user reaching up into admin territory, this is one regular user reaching sideways into another regular user's data. This matters enormously in multi-tenant systems. Think of a SaaS product where dozens of different companies all share the same application, each with their own private slice of data. If tenant isolation isn't enforced correctly on the server, a user from company A might be able to tweak a request and pull records that actually belong to company B. Same root cause as before, an ID or tenant identifier that's trusted from the client instead of being verified against who's actually logged in. The damage profile is different though. Instead of one broken record, you can end up leaking an entire other customer's data, which in a business context is a contractual and legal nightmare, not just an embarrassing bug. Whenever you're evaluating a multi-tenant application's security, this is one of the first questions worth asking. How, specifically, is the tenant boundary enforced on every single request? Access control problems aren't limited to web pages. They show up heavily in APIs too, and one common culprit is a misconfigured CORS policy. CORS, Cross-Origin Resource Sharing, is the browser-level rule that decides which external websites are allowed to make requests to your API and actually read the response. Done right, it's a tight allow list of trusted domains. Done wrong, say reflecting back whatever origin the request claims to be from, or just allowing everyone, and you've effectively opened your API's responses to any website on the internet, including one built by an attacker. Combine an overly permissive CORS policy with a user who's still logged into your real site in another browser tab, and a malicious page can silently ride along on that session and pull private data out through the API. APIs get hit by the same broken access patterns we already covered too: missing ownership checks, missing role checks. But they're easier to overlook because there's no visible button hiding anything. It's just raw endpoints, and a lot of teams simply don't audit every endpoint as carefully as they audit the pages users click through. So how do attackers actually go hunting for broken access control? It's refreshingly low-tech. The main technique is called parameter tampering, logging in as a normal, low-privilege account, capturing the requests the app normally makes using a proxy tool, and then simply editing the numbers and identifiers in those requests to see what the server lets through. Change an invoice ID, change a user ID, change a role field, replay the request, and watch the response. Another classic technique is forced browsing. Directly typing in URLs the interface never shows you, like /admin, on the theory that the page might still exist and still respond even though there's no link pointing to it anywhere. Neither technique requires exotic exploit code or deep technical sophistication. That's exactly what makes broken access control so dangerous at scale. Automated scanners can even run this kind of ID swapping systematically across an entire application. From an interview standpoint, this is worth remembering. Access control bugs are usually found through simple, methodical testing, not clever 0 days, which is also why they're so preventable with the right server-side discipline. It's worth pausing on why this particular category causes so much real damage. Because broken access control isn't about breaking cryptography or finding some rare memory corruption bug. The barrier to actually exploiting it is incredibly low, and the blast radius is often huge. A single unprotected admin endpoint can expose every customer's data at once, not just one account. A single IDOR in a healthcare or financial application can expose medical records or account balances that regulators care deeply about. And because these are logic flaws rather than software crashes, they're often invisible to traditional security scanners that look for known vulnerability signatures. A broken authorization check just looks like a normal, successful request from the server's point of view. That combination, easy to exploit, hard to automatically detect, and capable of exposing everything at once, is exactly why access control has consistently sat at or near the top of the OWASP top 10 for years. In interviews, if you're asked to name the highest impact, lowest effort category of vulnerability an attacker could find, broken access control is very often the right answer. So how do you actually defend against this? The foundational principle is deny by default. Every request should be rejected unless there's an explicit rule granting access, rather than allowed unless something explicitly blocks it. From there, enforcement has to happen centrally and on the server. Never trust a hidden button, a grayed out menu item, or anything living only in the browser, since all of that can be bypassed by simply crafting the request directly. Many mature applications implement this through a single shared access control component that every endpoint is forced to route through, rather than letting each developer hand-roll their own checks scattered across the code base, since scattered checks are exactly where individual pages get forgotten. Role-based or attribute-based access control models help make the rules explicit and auditable. Instead of ad hoc if statements buried in code, you get a clear policy of which roles can perform which actions. And finally, rate limiting and logging matter too. Even a well-defended system benefits from noticing when one account is rapidly cycling through thousands of sequential IDs, because that pattern alone is a strong signal someone is testing for IDOR right now. Let's bring it together. Broken access control is fundamentally about a missing or incomplete answer to one question asked on every single request. Is this specific authenticated user actually allowed to do this specific thing? We covered the core building blocks: authentication versus authorization, IDOR, vertical and horizontal privilege escalation, and API level gaps like broken cores, plus how attackers find them through simple parameter tampering and forced browsing, and how you defend against them with deny by default, centralized server-side enforcement. It sits at number 1 on the OWASP top 10 for 2025 precisely because it's common, cheap to exploit, and expensive to suffer. Next up in this series, we're moving to risk number 2, security misconfiguration. What happens when access control might be perfectly designed, but the systems running it are left with default passwords, open ports, or unnecessary features turned on? If you're prepping for a security interview or just want to understand how real-world breaches happen, subscribe so you don't miss it. Part 2. Security misconfiguration. Last video we covered broken access control, where the rules about who can do what are missing or wrong. This time we're covering something different, but just as common: security misconfiguration. Here, the security rules might be perfectly well designed, but the systems running them were never actually locked down. Think of a house with the state-of-the-art deadbolt on the front door, while a side window is left wide open. The lock isn't broken and nobody needs to pick it because there's an easier way in that nobody bothered to close. In software terms, this is what happens when a server, a framework, a cloud service, or an application is deployed with default settings, unnecessary features left switched on, or basic hardening steps skipped. It's one of the most common findings in real-world security assessments, precisely because it doesn't require a clever bug. No vulnerability had to be discovered. No code had to be broken. It just requires someone, somewhere, to not finish the job, to leave one setting at whatever it happened to be out of the box. The simplest form of misconfiguration is leaving default credentials in place. Routers, databases, admin consoles, and IoT devices frequently ship with a standard built-in username and password, meant to be changed on first setup. When that step gets skipped, anyone who knows the product also effectively knows the login, because the same default ships to every customer. This isn't theoretical. Entire botnets have been built by scanning the internet for devices still running their factory default admin password. The same pattern shows up with default configuration more broadly, not just credentials. A database installed with its sample accounts still active, an admin panel left reachable from the public internet, or a cloud service left at its permissive out-of-the-box settings are all instances of the same root problem. A secure default was possible, but the insecure factory state was simply never changed after deployment. Fixing this is rarely technically hard. It's a process and discipline problem, not a cryptography problem. Misconfiguration also shows up as things being left switched on that should have been switched off. Debug modes, sample applications, directory listing, and administrative interfaces are often enabled by default in development and simply forgotten when the system moves to production. Each extra enabled feature is one more thing an attacker can probe, and one more thing your team has to patch and monitor, whether anyone is actually using it or not. A closely related problem is overly detailed error messages. A stack trace that spills out internal file paths, database queries, or framework version numbers might be genuinely useful to a developer debugging locally, but shown to the public internet, it's a free reconnaissance report handed straight to an attacker. The right approach is to enable only what's genuinely needed for the application to function, and to show generic, minimal error messages externally, while keeping the detailed diagnostics in internal logs where only your own engineers can see them. Every response your server sends back to a browser can include a set of security headers, small instructions that tell the browser to enforce extra protections while rendering that page. Headers like a content security policy, which restricts what scripts are allowed to run, or HTTP strict transport security, which forces the browser to always use an encrypted connection, or a frame options header, which stops your page from being embedded inside someone else's malicious page for a clickjacking attack. None of these require rewriting your application. They are typically a handful of configuration lines on the web server or framework. And yet, because they are easy to forget and invisible when they're missing, a huge number of real production sites ship without them. The practical impact is that browsers, which are actually quite good at blocking whole categories of attacks, never get told to turn those protections on, leaving users more exposed than the underlying application code alone would suggest. One of the most damaging modern examples of security misconfiguration is cloud storage left accessible to the public. Cloud object storage buckets, essentially large folders hosted by a cloud provider for holding files, are private by default on most providers today. But a single wrong permission setting or a well-meaning developer trying to quickly share a file with a colleague can flip a bucket to public, meaning anyone on the internet with the address can read and sometimes write everything inside it. This single mistake has been behind a long string of major data breaches, exposing customer records, internal documents, and even source code and credentials. Not because anyone broke encryption or found a 0-day, an unknown, unpatched flaw nobody else has found yet, but because a storage container that should have stayed private was left wide open the entire time. The scary part is scale. Cloud infrastructure lets one misconfigured setting expose millions of records instantly. And because these buckets sit outside the application itself, separate from its actual code, they are easy for a security team to overlook when they are focused only on reviewing application code. Misconfiguration isn't only about a single wrong setting on day one. It's also about what happens over time. Systems drift. A server that was hardened correctly at launch can slowly fall out of date as patches are skipped, as manual changes pile up outside of version control, and as nobody schedules a regular review. Different servers in the same environment can end up running different software versions with different settings, simply because they were patched or configured at different times by different people. This drift matters because publicly known vulnerabilities get exploited automatically at scale, and an unpatched, out-of-date component is one of the easiest wins for an attacker running automated scans. Good practice treats infrastructure the same way we treat code: config defined once, version controlled, and redeployed consistently, rather than hand-edited server by server. So there's a single source of truth for what a secure configuration is supposed to look like everywhere. Finding misconfigurations is unfortunately very easy to automate. Search engines built specifically for scanning the entire internet let anyone look up every device or server exposing a particular open port, a particular default banner, or a particular unpatched software version, all without sending a single crafted attack. Attackers also run automated configuration scanners against known checklists. The same kinds of checks a security team would run against itself, testing for things like default credentials, open storage buckets, missing headers, and outdated software versions, all in bulk across huge ranges of the internet at once. Because none of this requires custom exploit development, misconfigurations tend to get found and abused extremely fast after they appear, sometimes within minutes of a system going live. That speed is exactly why continuous automated configuration checking on your own side has become essential, rather than a one-time review done only when a system is first launched. Defending against security misconfiguration starts with building one hardened baseline configuration, then deploying every server, container, and cloud resource from that same baseline instead of configuring each one by hand. This is what modern infrastructure as code practices are for. The secure settings live in a reviewed, version-controlled template, and machines are rebuilt from that template rather than manually patched in place, so drift has nowhere to creep in. On top of that baseline, unnecessary features, sample applications, and default accounts should be removed entirely, not just disabled. And every environment should get automated continuous scanning that checks for exactly the kinds of gaps we've covered: open storage, missing headers, outdated components, default credentials. Because these checks are simple and repeatable, they're ideal candidates for automation running on every deployment, rather than a manual review that only happens once a year during an audit. Let's bring it together. Security misconfiguration is what happens when the security controls you designed are never actually switched on, locked down, or kept up to date in the running system. We covered default credentials and default configs, unnecessary features and overly detailed error pages, missing browser security headers, publicly exposed cloud storage, and the slow drift of unpatched, inconsistent servers over time. We also covered how easily attackers automate the search for all of it and why the fix is a consistent, version-controlled, hardened baseline paired with continuous automated scanning rather than a one-time setup checklist. It sits near the top of the OWASP Top 10 for 2025 because it's everywhere, and because closing it is almost entirely a matter of process discipline rather than difficult engineering. Next up in this series, we're moving to risk number 3, software supply chain failures. What happens when the very components, libraries, and pipelines you build on top of turn out to be the weak link? If you're prepping for a security interview, subscribe so you don't miss it. Part 3: Software Supply Chain Attacks. We've covered broken access control and security misconfiguration, two ways a system you built can fail you. This time, we're looking at something you didn't build at all: the software supply chain. Modern applications are assembled, not written from scratch. A typical project pulls in open source libraries, build tools, container-based images, and continuous integration pipelines from dozens or hundreds of outside sources, then bolts on a relatively small amount of code that's actually yours. That's efficient, and it's why modern software gets built as fast as it does. But it means your security now depends on every one of those upstream suppliers behaving honestly and staying uncompromised. People and systems you likely never interact with directly. Picture a factory that trusts a supplier for one small part and never inspects it because it's always been fine before. If an attacker manages to tamper with that one part at the source, every finished product that ships afterward carries the tampering with it, automatically, at scale, without your factory ever doing anything wrong on its own line. That's the core danger of a software supply chain failure. The compromise happens somewhere you can't see, and it arrives already built into something you trusted by default. Before looking at how this goes wrong, it helps to be concrete about what the supply chain actually is. It's every third-party open source package your code imports, often nested many levels deep, since your dependencies bring their own dependencies with them. It's the build tools and compilers that transform your source code into something runnable. It's the container-based images you start a deployment from, which themselves bundle an entire operating system and its own set of packages. And it's the continuous integration and deployment pipeline itself, the automated system that takes your code, builds it, tests it, and pushes it live, usually with broad privileges to touch your production systems. Every one of these is a piece of software you're trusting, but almost never personally reviewing. A single popular utility library can be pulled in by millions of projects, which means a single compromise at that one point can ripple out to an enormous number of applications that never interacted with the attacker directly. The most direct attack on the supply chain is simply publishing a bad package or corrupting a good one. Typo squatting relies on developers making small typing mistakes, publishing a malicious package with a name almost identical to a popular one, hoping someone installs the wrong one by accident. Dependency confusion tricks a company's own build system into pulling a public package with the same name as an internal private one if the internal registry isn't configured to be checked first. And account takeover is arguably the most damaging. An attacker compromises the credentials of a legitimate maintainer and pushes a malicious update to a package that thousands of projects already trust and auto-update to. This has happened to real, widely used packages in major open source ecosystems, where a single hijacked maintainer account was enough to inject credential stealing code into a dependency chain used by an enormous number of downstream applications, all without a single line of the victim's own code ever being at fault. A second angle of attack skips your source code entirely and targets the build system itself. If an attacker compromises the CI/CD pipeline, the automated process that compiles, tests, and packages your software, they can inject malicious code during that build step, producing a tainted final artifact even though the source code in your repository looks completely clean. Because the pipeline is trusted to produce your official release, that tampered artifact often gets signed and distributed exactly like a legitimate one. This is precisely what happened in one of the most well-known supply chain attacks in recent history, where attackers compromised a vendor's build environment and inserted a backdoor into signed software updates, which were then automatically installed by thousands of that vendor's customers, including government agencies and major corporations, all of whom had no reason to distrust an update coming from a name they'd relied on for years. Not every supply chain compromise is a quick technical hack. Some are patient social engineering campaigns that unfold over months or years. A well-documented recent example involved a widely used open source compression library maintained largely by one volunteer. An unknown contributor spent a long stretch of time submitting genuinely useful patches, building trust, and gradually pressuring the maintainer, who was under real personal strain, until they were granted co-maintainer access. Only then did that access get used to slip a carefully obfuscated backdoor into the project's build scripts, code that was almost invisible in a normal source review and was only caught by chance before it spread widely. It's a sharp reminder that the supply chain isn't just packages and pipelines. It's also the humans who maintain them, and the trust relationships open source runs on can themselves be a target. A big supply chain attacks go unnoticed for so long is that most organizations simply can't answer a basic question. Exactly what components and which versions of them are actually running in production right now? Without a software bill of materials, essentially an ingredient list for your software, teams have no fast way to check whether they're affected when a popular library is suddenly found to be compromised. And without cryptographic provenance, proof of exactly which source code and build process produced a given artifact, there's no reliable way to verify that what you're running is actually what you think it is, rather than something quietly substituted along the way. This gap is exactly why frameworks like SLSA, short for Supply Chain Levels for Software Artifacts, have emerged. Standardized ways to attest verifiably that a build followed a trusted process and wasn't tampered with in transit. What makes supply chain failures so uniquely dangerous compared to a bug in one company's own code is the blast radius, the total size and reach of the damage a single compromise can cause. A vulnerability you introduce yourself typically affects only your own application. A vulnerability or a deliberate backdoor in a widely used shared dependency affects every single application that pulled it in, often automatically through routine dependency updates that nobody manually reviewed before accepting. That means an attacker doesn't need to breach your specific organization at all. They only need to compromise one well-placed, widely trusted upstream component, and they inherit access to an enormous and diverse set of downstream victims for free, without ever having to individually target a single one of them. This is why security researchers increasingly treat popular open source maintainers and widely used build infrastructure as high-value targets in their own right, deserving the same level of protection and scrutiny normally reserved for a company's own production systems, even though those maintainers are often unpaid volunteers with none of that support behind them. Defending against supply chain failures means treating your dependencies with the same discipline you apply to your own code. Start by maintaining a software bill of materials for every application, an accurate, automatically generated inventory of every component and version in use, so that when the next widely used library turns out to be compromised, you can find out in minutes whether you're affected instead of days. Require cryptographic signing and provenance attestation on build artifacts, so a tampered or substituted package can actually be detected rather than silently trusted. Lock dependency versions instead of always pulling the newest release automatically. Review updates before they land, and run continuous automated scanning that checks your dependency tree against databases of known compromised and known vulnerable packages. And harden the build pipeline itself, limiting who and what can modify it, since as we covered, the pipeline can be just as valuable a target to an attacker as your source code. Let's bring it together. Software supply chain failures happen when the trust you place in outside packages, build tools, container images, and pipelines gets betrayed somewhere upstream of your own code, whether through a maliciously published package, a hijacked maintainer account, a compromised build system, or a patient social engineering campaign against an open source volunteer. What makes it especially dangerous is the blast radius. One compromised, widely trusted component can silently reach an enormous number of downstream applications at once. The fix is verification and visibility, knowing exactly what you're running through a software bill of materials, verifying builds cryptographically, scanning dependencies continuously, and hardening the pipeline itself, rather than blindly trusting that upstream software is safe just because it always has been before. Next up in this series, we're moving to risk number 4, cryptographic failures. What happens when the encryption meant to protect your data is missing, outdated, or implemented incorrectly? If you're prepping for a security interview, subscribe so you don't miss it. Part 4. Cryptographic failures. We've covered access control, misconfiguration, and the supply chain. Now we're covering the mechanism that's supposed to protect your data even after everything else has already gone wrong. Cryptography, the science of scrambling information so only someone holding the right secret can unscramble it again. A cryptographic failure isn't necessarily the total absence of a lock. It's often a lock that only looks like real protection. Think of a child's diary with a tiny clasp lock on it versus a bank vault. Both are technically locked, but the diary lock can be popped open with a fingernail, while the vault is built to resist serious, sustained attack from someone who really wants what's inside. In software, this is exactly what happens when sensitive data, like passwords, personal information, or payment details, is protected with encryption or hashing that looks fine on the surface, but is actually outdated, misconfigured, or missing entirely. The data was never truly exposed on purpose. Nobody skipped a step out of malice, but the protection wasn't strong enough to survive contact with a real attacker who actually goes looking for the weak spot. Cryptography in a typical application does two related but distinct jobs. It protects data at rest, meaning information sitting in a database, a file, or a backup, so that anyone who gets unauthorized access to the storage itself still can't read it. And it protects data in transit, meaning information moving across a network, between a user's browser and your server, or between two of your own internal services, so that anyone intercepting that traffic sees only scrambled bytes. Both matter, and they fail in different ways. A system can have excellent encryption in transit using modern TLS everywhere, while still storing that same data completely unencrypted once it lands in the database. Or the reverse, solid database encryption undermined by sending the same data over plain unencrypted connections beforehand. A cryptographic failure often hides in exactly this kind of gap, one link in the chain that quietly wasn't protected the way the rest of the system assumed it was. Cryptographic algorithms age, sometimes badly. Hash functions and ciphers that were considered perfectly reasonable years ago can later be proven mathematically weak or simply become fast enough to brute force as computing power grows. MD5 and SHA-1, once common for hashing, are now considered broken for security purposes since researchers have demonstrated practical ways to produce two different inputs with the same hash, defeating their entire purpose. Older symmetric ciphers like single DES use key sizes far too short for modern hardware, which can now try every possible key in a feasible amount of time. The uncomfortable truth is that code written to a perfectly reasonable standard a decade ago can become a cryptographic failure today, purely because the algorithm itself didn't age well, not because anyone implementing it made a mistake at the time. This is exactly why cryptographic agility, the ability to swap algorithms without a full rewrite, matters so much. Sometimes the failure isn't a weak algorithm, it's no algorithm at all. Applications still occasionally transmit sensitive data over plain unencrypted HTTP instead of HTTPS, or store entire database columns like social security numbers or health records completely in plain text with no encryption applied whatsoever. Anyone positioned to intercept that network traffic or anyone who gains read access to that database sees the raw sensitive data directly. No cracking or cryptanalysis required. This often happens quietly through an internal API that was never meant to be public but became reachable anyway. A legacy feature that predates the company's security policy, or a new field added to a database table without anyone updating the encryption at rest configuration to cover it. Because there's no broken lock to notice, just an absent one, this kind of failure often survives far longer in a system than a weak algorithm would, since nothing about it visibly resembles security at all. Even when the right algorithm is used correctly, cryptography still depends entirely on keeping the encryption key secret, the value that actually locks and unlocks the data. And key management is where a huge number of real-world failures actually happen. A shockingly common mistake is hard-coding an encryption key or an API secret directly into source code. That code then gets pushed to a shared repository, sometimes a public one, and the key is exposed to anyone who can read it, permanently, since it typically stays in the commit history even after someone notices and removes it later. The old exposed version doesn't disappear just because a new one replaced it. Similarly, encryption keys that never get rotated, that are reused across every customer or every environment, or that are stored in the same place as the data they're meant to protect, all defeat the actual purpose of having a key in the first place. A lock is only as good as how well its key is kept away from everyone but its owner. Good key management means keys live in a dedicated, access-controlled secrets system, are rotated on a schedule, and are never something a developer needs to see, copy, or paste. Modern encryption schemes often rely on a random value, such as an initialization vector or a nonce, that's supposed to be unpredictable and used only once. If a system generates that value using a weak, non-cryptographic random number generator, or worse, reuses the exact same value repeatedly, the mathematical guarantees the encryption scheme depends on can quietly collapse, even though the underlying algorithm itself is perfectly strong. An attacker who can predict or observe a repeated initialization vector can sometimes recover meaningful information about the encrypted data, or in some cipher modes, break the encryption outright. This is a subtle failure precisely because the code appears to be using strong modern encryption correctly. The flaw isn't in the cipher, it's in the randomness feeding it, which is why cryptographic libraries insist on a cryptographically secure random source, not a general purpose one meant for things like shuffling a list or generating a game seed. Once an attacker has a copy of encrypted or hashed data, whether stolen from a breached database or intercepted off the network, cracking a weak scheme is often just a matter of applying the right tool. For weak or unsalted password hashes, pre-computed rainbow tables let an attacker look up a hash and instantly recover the matching plaintext password for huge numbers of common passwords at once. No real computation required at attack time. For outdated ciphers or short keys, modern hardware, including cloud computing rented by the hour, makes brute force key search genuinely practical rather than theoretical. And where a downgrade is possible, some attackers will manipulate a connection into falling back to an older, weaker version of a protocol that a server still supports for compatibility, then break that weaker version instead of the strong one. None of this requires the attacker to defeat modern cryptography itself. It only requires finding the one place where modern cryptography wasn't actually being used. Defending against cryptographic failures starts with using only modern, well-vetted algorithms, encrypting everything sensitive both in transit and at rest, and retiring outdated ones like MD5 or single des the moment they're found in a codebase, rather than waiting for an incident to force the issue. Keys need a real home, a dedicated key management system or hardware security module, with rotation, strict access control, and full separation from the data they protect, instead of living in source code or configuration files. Passwords, specifically, should never be encrypted or hashed with a fast general-purpose hash function. They need a slow, purpose-built password hashing algorithm like bcrypt, scrypt, or argon2, combined with a unique salt per password, specifically designed to make large-scale cracking attempts prohibitively slow even if the hash database is stolen. None of this requires inventing new cryptography yourself, which is itself a common and dangerous mistake. It requires correctly using the well-tested cryptography that already exists. Let's bring it together. Cryptographic failures happen when the protection meant to guard sensitive data turns out to be outdated, missing, mismanaged, or undermined by weak randomness, even when everything looks fine on the surface. We covered outdated algorithms like MD5 and single DES, data left completely unencrypted, hard-coded and poorly managed keys, and weak randomness quietly breaking otherwise strong encryption schemes. We also covered how attackers exploit each of these, from rainbow tables to brute force key search to protocol downgrades. The fix is almost always the same. Use modern, well-vetted cryptography correctly, manage keys through a dedicated system instead of source code, and never invent your own algorithm. Next up in this series, we're moving to risk number 5, injection. What happens when untrusted input gets treated as code or commands instead of plain data? If you're prepping for a security interview, subscribe so you don't miss it. Part 5, injection. We've covered access control, misconfiguration, the supply chain, and cryptography. Now we're looking at one of the oldest and most reliably damaging categories in application security, injection. Imagine handing a waiter a simple order slip, except somewhere on that slip, mixed in with your food order, you've also written an instruction for the kitchen to hand you the cash register. If the kitchen can't tell the difference between the actual order and an instruction hidden inside it, it might just follow both, because to the kitchen, it's all just text on the same slip of paper. That's injection in a nutshell. It happens whenever an application takes data that a user typed in and instead of treating it purely as data, ends up executing part of it as a command. The application never meant to give anyone that kind of control. It just failed to keep the user's words and its own instructions clearly separated. And that one blurred line is enough to hand an attacker capabilities the application's designers never intended anyone outside it to have. Most applications work by taking something a user typed, a search term, a username, a file name, and using it to build a command that gets handed to another system, a database, an operating system shell, an LDAP directory, essentially a specialized database many organizations use to store and look up things like employee accounts, email addresses, and permissions, or an XML parser, a component that reads structured documents. The failure happens when that user-supplied text is inserted directly into the command's own syntax, rather than being kept clearly separate as pure data. If a user's input can contain characters that have special meaning to whatever's interpreting the command, like a quote character that ends a string early in a database query, that input stops being just a value and starts being part of the instruction itself. The receiving system has no way to know the difference. It just parses whatever text arrives and executes exactly what the resulting command says, extra clauses and all. The classic example is SQL injection against SQL, the standard language nearly every relational database uses to store and retrieve data. Say a login form builds a database query by directly pasting the entered username and password into a query string. A well-known attack is typing something like a single quote followed by or1 equal to 1 into the username field. If that text is inserted straight into the query without protection, it can rewrite the query's actual logic, turning a check for "does this exact username and password match" into something that's always true regardless of what was typed, letting an attacker log in as any user without ever knowing a real password. The same underlying flaw lets attackers read data they were never authorized to see, modify or delete records, and in the worst cases, execute administrative commands on the database server itself. SQL injection has been a top-ranked risk for over 2 decades, not because it's exotic, but because string building queries by hand remains a very easy trap to fall into, and one that looks perfectly harmless right up until someone tests it with the wrong input. Injection isn't limited to databases. Command injection happens when an application takes user-supplied text like a file name or an address and passes it into a system shell command, an instruction sent directly to the underlying operating system, to do something like convert a file or ping a host. Operating system shells treat certain characters like a semicolon or a pipe symbol as separators between multiple commands, a normal and useful feature for a person typing at a real terminal. If an attacker's input contains one of those characters followed by their own command, and the application builds the shell command through simple string concatenation, gluing pieces of text together, the shell will happily run the attacker's command right after the intended one, with no way to tell that one of them wasn't supposed to be there. Depending on what account the application runs as, this can let an attacker read arbitrary files, create new user accounts, or gain a foothold to run further commands on the server, turning what looked like an innocent file conversion feature into full remote code execution. The same underlying mistake, mixing untrusted input directly into a command's syntax, shows up wherever an application talks to an interpreter. NoSQL databases have their own query syntax that can be manipulated in similar ways to SQL, letting an attacker alter query logic even though there's no traditional SQL involved at all. Applications that check credentials against an LDAP directory can be tricked with specially crafted input into altering the directory search filter itself. Applications that parse XML input from users can be attacked with maliciously crafted entity references that make the parser read local files or reach out to internal network resources it was never meant to touch. None of these are really separate problems. They're the same root cause showing up in a different interpreter, which is exactly why injection is treated as one broad category rather than a list of unrelated bugs. Given how long this problem has been understood, it's fair to ask why injection still ranks among the most common serious vulnerabilities found in real applications. Part of the answer is simply that building a query or command by directly gluing pieces of text together is the most obvious, intuitive way to write that code, especially for a developer under time pressure who isn't thinking about attacker input at that moment. It's the version that just naturally comes to mind first. Part of it is legacy code. Systems written years before secure coding standards were as widely taught that still handle input the old way and never get revisited unless something visibly breaks. And part of it is unclear trust boundaries. A value that was already validated somewhere else in the system gets reused later in a different context without anyone rechecking whether it's actually still safe there. Safety in one context doesn't automatically transfer to another. Injection rarely survives because developers don't understand the risk anymore. Most do. It survives because one unguarded seam, one place where the old habit slipped through, is often all it takes. Exploiting injection rarely requires deep system access to begin with. Just a form field, a URL parameter, or an API request the attacker can freely send input to. Attackers and the automated scanning tools they use systematically try known special characters and payloads against every input point a target application exposes, watching for anything unusual in the response, like a database error message leaking table names, or a noticeably longer delay that hints a crafted condition was actually evaluated. Once a working injection point is found, techniques exist to extract an entire database's contents one carefully targeted query at a time, even when the application shows no visible errors at all, a technique known as blind injection. What starts as one overlooked input field can end with an attacker walking away with an entire customer database, or a shell on the underlying server. The single most effective defense against injection is to stop building commands by gluing text together at all. Parameterized queries, sometimes called prepared statements, and safe APIs provided by modern ORMs, object relational mappers, tools that let a developer work with database records as ordinary code objects instead of writing raw query text by hand, send the user's data to the database completely separately from the query's actual structure. So the database always knows exactly which parts are data and can never confuse them with instructions, no matter what characters they contain. Strict input validation allow listing expected formats rather than trying to block known bad characters adds a second layer, catching malformed input before it ever reaches an interpreter. And because no defense is perfect, database accounts used by applications should follow least privilege. A web application's database login should never have permission to drop tables or read unrelated databases, so that even a successful injection is contained to only what that limited account can actually do. A web application firewall can help catch known attack patterns, but it's a supplement to these fixes, never a replacement for them. Let's bring it together. Injection happens whenever untrusted input gets treated as part of a command instead of plain data, letting an attacker rewrite the logic of a query, a shell command, a directory lookup, or a parser. We covered SQL injection rewriting login logic, command injection turning a file conversion feature into remote code execution, and the same root cause showing up in NoSQL, LDAP, and XML parsers. We covered why it persists, string concatenation, legacy code, and unclear trust boundaries, and how attackers exploit it, from error-based probing to fully blind data extraction. The fix is consistent. Separate data from commands using parameterized queries and safe APIs. Validate input strictly and limit what a compromised component can actually do. Next up in this series, we're moving to risk number 6, insecure design. What happens when a system is vulnerable by architecture before a single line of code is even written? If you're prepping for a security interview, subscribe so you don't miss it. Part 6, Insecure Design. We've spent this series on injection, cryptographic failures, misconfiguration, and the supply chain. Flaws that show up when code is written or configured incorrectly. Something a specific fix in a specific file can address. Insecure design is different. Imagine a construction crew building a house perfectly, exactly to the blueprint. No shortcuts, no mistakes, and the house still ends up with no lock on the front door, because nobody ever drew one on the plan in the first place. The builders didn't fail, the plan failed. That's the core idea behind insecure design. It's not a bug you can patch, because there's no broken line of code to point to. Every line does exactly what it was written to do. The application is working exactly as designed, and the design itself never accounted for how someone might abuse it, which is what makes this category harder to fix than the others in this series. There's no single patch, only a rethink. It helps to separate these two categories clearly. An implementation bug is something like a missing input check that lets injection through. The design was fine, a specific line of code wasn't. You find it, you patch that one spot, and the fix is done. The rest of the system is untouched. A design flaw is structural. It lives in the shape of the whole workflow, not in any one line. Think of an online store that lets a customer apply a discount code, then lets them go back a step and apply a second, different discount code on the same order, because nobody ever decided a single order should only accept one discount. There's no single buggy line to fix here. Every individual step of that checkout was coded correctly. The checkout workflow itself needs to be rethought, because the business rule, one discount per order, was never actually designed into the system in the first place. It simply never occurred to anyone to write it down as a rule. That discount stacking example is a real category called business logic abuse, and it's one of the clearest signatures of insecure design. Business logic just means the rules that encode how the business is actually supposed to work. One discount per order, one seat per booking, and every step in the checkout flow works exactly as intended in isolation. Applying a discount code is a legitimate, tested feature on its own. The flaw only appears when someone realizes the workflow lets them repeat a step the designers assumed would only ever happen once. The same pattern shows up in things like a password reset flow that lets an attacker request unlimited reset codes with no cooldown between attempts, or a ticket booking flow that never checks whether the same seat was already reserved by two people at the exact same moment. None of these trigger an error message anywhere. The system just does precisely what it was told to do, because it was never told not to do it. Another common design flaw is trusting that a multi-step process will always be used in order when nothing in the system actually enforces that assumption. Picture a checkout with 3 steps: choose items, enter payment, confirm order. If the final confirm order step only checks that a payment step exists somewhere in the session, rather than actually re-verifying that payment succeeded, an attacker can call the confirmation step directly, skipping payment entirely, and the order goes through anyway. The individual steps were all coded correctly. Each one does its own job properly. The design simply assumed a well-behaved browser walking through the steps in the expected sequence, clicking each button in order, and never accounted for someone calling the steps directly out of order, which is trivial to do against any web API using nothing more than a basic scripting tool. The fix for insecure design isn't a code review. It's a step that has to happen earlier: threat modeling. This means sitting down with a proposed design before a single line of code is written and deliberately asking how someone with bad intentions could abuse each step. What happens if this request is sent out of order? What happens if this quantity field is negative? What happens if this action is repeated 1,000 times in a row? Doing this well for a whole system means having some structure so nobody just relies on inspiration to catch every angle. Frameworks like Stride exist for exactly that. It's an acronym and checklist for 6 categories of abuse to walk through for each part of a design. Things like someone impersonating another user, someone tampering with data in transit, or someone escalating their own privileges beyond what they should have. One category at a time, systematically, instead of relying on someone happening to think of it on their own. Skipping this step doesn't create a visible gap anywhere. It just means nobody ever asked the question, and the resulting design quietly assumes every user will behave exactly as expected. Insecure design persists for reasons that have very little to do with skill. Teams under pressure to ship a feature quickly design for the happy path, the one sequence of steps a well-intentioned user is expected to follow, and rarely budget time to sit down and imagine deliberate misuse before the deadline arrives. Requirements documents describe what the system should do: add to cart, apply a code, pay, confirm, but rarely describe what it must never allow. So there's no checklist forcing anyone to consider abuse cases alongside the normal ones. And in many organizations, security expertise is still brought in only at the code review or penetration testing stage, long after the architecture is already locked in and expensive to change, which means the best opportunity to catch a design flaw before it's built at all has already passed by the time anyone with that expertise even looks at it. Exploiting a design flaw rarely involves any hacking tool at all. No injected payload, no cracked password, nothing that would trip a typical security scanner. An attacker simply studies how the application is meant to be used, reads its documented workflow or public API, or just clicks through it themselves like any normal customer, and looks for a step that was assumed but never enforced. A limit that's checked on the screen but not on the server. A sequence that's suggested by the interface but not actually required by the backend. Once they find that gap, the abuse is often trivially automated, scripting the discount stacking trick to run thousands of times in a row, or hammering a password reset endpoint with no rate limit until it yields something useful. The system tips entirely in the attacker's favor, using only the features the application intentionally provides, which is exactly why this kind of abuse is so hard to catch with tools built to look for broken code instead of misused workflows. Defending against insecure design starts before any code exists. Threat modeling a proposed feature, deliberately walking through how it could be abused, using something like the stride checklist from earlier, catches the discount stacking or skip a step problems while they're still cheap to fix on paper, before a single developer has written a line for it. Writing explicit abuse cases alongside the normal use cases. A user should not be able to apply 2 discount codes. A user should not be able to confirm an order without a successful payment, turns an unspoken assumption into a requirement someone actually has to build and test against, the same way a use case does. And every rule that matters, quantity limits, rate limits, step ordering, has to be enforced on the server, never just suggested by the interface. Because anything left to the client's good behavior can simply be skipped by anyone willing to send requests directly to the backend instead of clicking through the actual app. Let's bring it together. Insecure design is what happens when a system is vulnerable by its own blueprint, not because of a broken line of code, but because nobody ever designed against abuse in the first place. We covered how it differs from an implementation bug, business logic abuse like discount stacking, workflows that assume steps happen in order when nothing actually enforces that, and why it persists, shipping speed, happy path thinking, and security arriving too late to influence the architecture once it's already locked in. The fix is to threat model before building, using a structured framework like Stride so the exercise doesn't depend on someone's luck. Write abuse cases alongside use cases, and enforce every meaningful rule on the server, never just in the interface where it can be trivially bypassed. Next up in this series, we are moving to risk number 7, authentication failures. What happens when a system can't reliably prove who it's actually talking to? If you're prepping for a security interview, subscribe so you don't miss it. Part 7, authentication failures. Every application eventually has to answer one question before it does anything else. Who exactly is on the other end of this request? Authentication is the process of proving that, of turning a claim, "I am this user," into something the system can actually verify. It sounds simple. Show a username and password, get let in. But the ways that process can be built weakly are numerous and, historically, catastrophic. Authentication failures happen whenever a system can be tricked into believing someone is who they claim to be, without properly verifying it. A stolen password gets accepted with no second check. A session token can be guessed. A login form can be hammered with thousands of password guesses with nothing stopping it. Once identity itself can't be trusted, every other protection built on top of it, access control deciding what you're allowed to do, authorization enforcing it, logging recording it, starts from a false premise. Because all three assume the system already correctly knows who you are. The most basic authentication failure is simply weak credentials. Passwords short enough to guess in seconds, or default admin passwords, the ones printed in a setup manual that were never changed after installation. Closely related is credential reuse, the same password used across many different sites, which becomes dangerous the moment any one of those sites is breached and its password list leaks online, often traded and sold in bulk. Attackers take those leaked username and password pairs and try them automatically at high speed against banks, retailers, and email providers in an attack called credential stuffing, betting correctly that a meaningful fraction of people reused that exact password somewhere else. The application being attacked did nothing wrong technically. Its authentication just had no way to tell a legitimate login from an attacker holding a stolen, perfectly valid password, because as far as the login form can see, the password is correct. If a login form has no limit on failed attempts, an attacker can simply try password after password automatically, thousands of times a minute, until one works, a brute force attack. This works far faster than most people expect against short or predictable passwords, and it's entirely preventable with something as simple as locking an account or at least slowing responses after a handful of failed tries. The other major gap here is relying on a password as the only factor at all. Multi-factor authentication, requiring something you know, the password, alongside something you have, like a one-time code from a phone or a physical security key, means that even a correctly guessed or stolen password isn't enough on its own to get in. Skipping MFA, especially for sensitive accounts, leaves a system exactly one leaked password away from full compromise, with no second obstacle in the attacker's way at all. Passwords aren't the only piece of identity that has to be protected. After a successful login, a system issues a session token, essentially a temporary claim of "this browser is already authenticated," so the user isn't asked to log in again on every single click. If that token is predictable, guessable from a pattern, transmitted without encryption where it can be intercepted, exposed in a URL that gets logged or shared, or simply never expires, an attacker who obtains it can impersonate the logged in user without ever needing a password at all, a technique called session hijacking. A related flaw, session fixation, tricks a user into authenticating under a session ID the attacker already knows in advance. So the moment the victim logs in, the attacker's copy of that same ID becomes valid too. Either way, the server ends up trusting a token it can no longer be sure actually belongs to who it thinks it does. Authentication failures persist partly because every extra security step adds friction, and product teams are often, understandably, reluctant to make logging in harder where it might cost them users who give up and leave. Multi-factor authentication gets built as an optional setting a user can turn on rather than a default, which means most people, faced with one more step to enable, simply never do it. Password policies get relaxed to avoid frustrating users, even though that trade-off directly increases the odds that a weak, guessable password gets chosen in the first place. And session lifetimes are frequently set far longer than they should be for convenience, so a user isn't logged out mid-task, leaving a stolen or exposed token useful to an attacker for days or weeks instead of minutes. None of these are exotic mistakes. They're ordinary trade-offs between convenience and security, repeatedly resolved in convenience's favor, one reasonable sounding decision at a time. Most authentication attacks today don't involve cleverness so much as scale. Attackers start with enormous lists of usernames and passwords leaked from unrelated breaches, freely traded online for very little money, and run them automatically against the login pages of banks, retailers, and social media platforms, using purpose-built tools designed exactly for this. Because password reuse is common, even a modest success rate, a small fraction of a percent, against a list of millions of credentials, still yields a large number of working logins. Once an account is taken over, an attacker can drain stored payment methods, impersonate the user to their contacts to run further scams, or use that one compromised account as a foothold to pivot into other, better protected systems the victim happens to also use with the same reused password. It's less a single skilled hacker and more an assembly line running continuously against whatever the weakest link happens to be. The most effective single defense here is multi-factor authentication and making it the default rather than an opt-in setting. So a leaked password alone is no longer enough to get in on its own. Rate limiting and progressively locking out repeated failed login attempts shuts down brute force and credential stuffing attacks without meaningfully inconveniencing a legitimate user who mistypes a password once or twice. Underneath all of that, passwords must be stored using a slow, salted hashing algorithm designed specifically for passwords. One-way math that turns a password into a scrambled value that can be checked but never reversed, never encrypted, or worse, stored in plain text, so that even a full database breach doesn't hand attackers usable credentials. And session tokens should be long, random, unguessable by brute force, transmitted only over encrypted connections, and set to expire after a reasonably short period of inactivity, limiting how long a stolen token stays useful to whoever took it. Let's bring it together. Authentication failures happen whenever a system can be tricked into trusting an identity it never properly verified through weak or reused passwords, brute forcible login forms with no second factor, or session tokens that can be stolen or guessed. We covered why it persists, usability trade-offs, MFA treated as optional, sessions left alive too long, and how attackers exploit it at scale using massive leaked credential lists and automated tools rather than any real cleverness. The fix is consistent. Make multi-factor authentication the default. Rate limit login attempts, hash passwords with a proper algorithm designed for exactly that purpose, and keep session tokens short-lived and encrypted in transit. Next up in the series, we're moving to risk number 8, software or data integrity failures. What happens when a system trusts an update or a piece of data it never actually verified? If you're prepping for a security interview, subscribe so you don't miss it. Part 8. Software and data integrity failures. Most software updates itself constantly. Patches, plugins, packages pull down automatically in the background, usually without you ever clicking a single button. All of that convenience rests on one assumption, that the thing you just downloaded and are about to run is actually what it claims to be, unmodified from a legitimate source and not something an attacker slipped into the delivery chain along the way. Software or data integrity failures happen whenever a system trusts code or data without verifying it wasn't tampered with, an update installed without checking a cryptographic signature, a serialized object from an untrusted source deserialized and executed blindly, or a build pipeline that will happily package and ship whatever gets pushed into it, no questions asked. When integrity checks are missing, an attacker doesn't need to break in through the front door. They just need to corrupt something the system already trusts and let that trust do the work of walking straight in on its own. Integrity in security terms is different from confidentiality. It's not about keeping data secret. It's about proving that data or code hasn't been altered since it was created or last approved. Secrecy and integrity are two entirely separate properties, and a file can be fully public and still need its integrity verified. The standard tool for this is a digital signature. The publisher signs the software or data with a private key that only they hold, and anyone receiving it can verify that signature with the matching public key, which is safe to share freely. If even a single byte was changed after signing, the signature no longer matches and verification fails. That's the whole point. The math is built so tampering can't go unnoticed. A system with proper integrity checks treats every unverified signature as a hard rejection, not a warning to click past. The failure mode this category describes is exactly that, a signature that could have been checked but simply wasn't. Applications often convert objects into a serialized format, essentially a flattened byte stream that captures an object's entire internal state to send them across a network or store them for later. Then deserialize them back into a live working object when needed. The danger is that deserializing untrusted data can, in many programming languages and frameworks, trigger code execution as a side effect of simply rebuilding that object. Before any of the application's own logic even runs, the damage happens during the act of unpacking, not afterward. An attacker who can control the serialized bytes being deserialized can craft a payload that, once reconstructed, executes arbitrary commands on the server, essentially smuggling a program inside what looks like ordinary data. This is why serialized data from an untrusted source, a user upload, a cookie, an API parameter, should never be deserialized directly without strict validation, or avoided entirely in favor of simpler formats like JSON with a fixed checked schema that can't be coaxed into running code just by being read. Auto-update mechanisms are a favorite target precisely because they are built to run with high trust and little friction. A device or application is designed to accept whatever the update channel serves it. That's the entire point of the feature. No prompts, no confirmation dialogues. If that channel doesn't cryptographically sign its updates, or the client doesn't verify the signature before installing, an attacker positioned on the network, or one who has compromised the update server itself, can substitute a malicious package for the legitimate one, and the device has no way to tell the difference. Because the whole point of auto-update is to install without asking the user, a successful substitution here can compromise every device that checks in for updates all at once, with no user interaction required at all, turning a single point of trust into a single point of failure for an entire user base. Modern software is built and deployed through automated pipelines. Code gets committed, tests run, and a build gets packaged and shipped, often with no human looking at every single step along the way. If that pipeline itself isn't locked down, unsigned commits accepted from anyone, build servers with weak access control, no verification that the artifact leaving the pipeline actually matches what was reviewed and approved, then compromising the pipeline just once means compromising every release that comes out of it afterward, silently, for as long as the tampering goes unnoticed. This is exactly the kind of integrity failure behind some of the most damaging software supply chain incidents on record. Not a flaw in the final product's code itself, but a lack of verification in the process that built and shipped it, which is precisely why it's so hard to catch by reviewing the code alone. Integrity checks add a step, and teams under pressure to ship quickly often treat signature verification, deserialization safety, and pipeline hardening as things to add later once there's time, which in practice tends to mean never. Many popular serialization libraries also made unsafe deserialization the default behavior for years, so plenty of code inherited the risk without any developer ever making an explicit unsafe choice. They just used the library the way its own documentation showed. And because a missing integrity check doesn't cause a visible problem until an attacker specifically exploits it, it's an easy category to deprioritize against features users can actually see. Nothing looks broken, right up until it very much is. And by then, the tampering may already be shipped to every user. Attackers specifically look for the weakest link in a trust chain. An update channel with no signature verification, a public endpoint that deserializes attacker-controlled data, or a build server with lax access control that a phishing email or a leaked password could open right up. Once found, the appeal is leverage, compromising a single shared point, one update server, one build pipeline, one widely used library that thousands of other projects quietly depend on, can silently compromise every downstream system that trusted it without question. This is what makes integrity failures so attractive at scale. The attacker does the work once, and the trust relationship they abused does the rest of the distribution for them automatically, exactly as it was designed to, just for the wrong recipient. The core fix is straightforward to state, though it takes discipline to apply everywhere. Sign software and data at the source, and actually verify that signature before trusting anything downstream, updates, packages, and container images included. Treating an unsigned or unverifiable artifact as a rejection, not a formality. Build pipelines need the same hardening as production systems. Restricted access, required code review, and reproducible builds, meaning the same source code always produces a verifiably identical build, so what ships can be checked against what was reviewed. And wherever possible, avoid deserializing untrusted data in unsafe formats altogether. Prefer simple structured formats like JSON validated against a strict schema. And if a legacy system truly needs binary deserialization, isolate it in its own restricted environment and limit what object types it's ever allowed to reconstruct. Let's bring it together. Software or data integrity failures happen whenever code or data is trusted without verifying it wasn't tampered with, unsafe deserialization of untrusted objects, auto updates installed without a signature check, or a build pipeline that ships whatever gets pushed into it with nobody checking the output against what was reviewed. It persists because verification steps get deprioritized under time pressure, and because the damage stays completely invisible until an attacker specifically targets that missing check, at which point one compromise can silently ripple out to every downstream system that trusted it. The fix is to sign and verify everything. Harden the build pipeline itself the same way you'd harden a production server, and avoid unsafe deserialization in favor of strict validated data formats like schema-checked JSON. Next up in this series, we're moving to risk number 9, security logging and alerting failures. What happens when an attack succeeds and nobody in the system ever finds out? If you're prepping for a security interview, subscribe so you don't miss it. Part 9. Security logging and alerting failures. Here's an uncomfortable statistic. At organizations that get breached, it often takes many months, on average well over half a year historically, before anyone even realizes an attacker was inside. Not because the attacker was flawless, but because the systems that should have noticed, logs, alerts, monitoring, either weren't recording the right events or were recording them into a pile nobody ever looked at. A log, for anyone who hasn't worked with one directly, is just a time-stamped record of what happened, who logged in, what they clicked, what request hit the server, and when. Security logging and alerting failures happen whenever a system can't detect or can't surface evidence that something has gone wrong. It's a different kind of failure than the others in this series. It's not about preventing the initial break-in, it's about what happens after, and whether anyone finds out before the damage compounds into something far larger than the original intrusion. Certain events are considered security relevant almost everywhere. Successful and failed login attempts, access control failures, like someone repeatedly trying to reach a resource they're not authorized for, and high-value actions, large transactions, permission changes, data exports. When a system doesn't log these at all, there's no record to investigate after the fact. No way to reconstruct what an attacker did, when they did it, or what they touched. The investigation simply hits a wall of silence exactly where the answers should be. This isn't about logging everything. That creates its own problem. A mountain of noise nobody can search through. Buried in it are so many irrelevant entries that the important ones become impossible to find. It's about consistently capturing the handful of event types that actually matter for detecting and investigating an incident. Generating logs is only half the job. Plenty of breached organizations had the relevant events logged the entire time. The evidence existed, sitting right there in a file somewhere, but nothing was reviewing it in anything close to real time. Without automated alerting rules that flag suspicious patterns, a burst of failed logins, access from an unusual location, a spike in data downloads, those logs just accumulate as a static archive that only gets consulted after someone already suspects a problem, which is exactly backwards from how detection is supposed to work. Effective monitoring means an unusual pattern should trigger a signal to a human, automatically the moment it happens, not wait for someone to go looking days or weeks later once the damage is already done and the trail has gone cold. A capable attacker, once inside, often goes straight for the logs themselves, precisely because they know an investigator will eventually come looking there. If logs are stored on the same system an attacker has compromised, and that attacker has enough privilege, they can simply delete or edit the entries that would reveal their activity, covering their tracks on the way out. The same way a burglar might disable the security camera before searching the house. This is why log integrity matters as much as log collection. Logs should be written to a separate, access-restricted system as close to real-time as possible, ideally append only, meaning entries can be added but never edited or deleted afterward, so that compromising the original server doesn't also hand the attacker the ability to erase the evidence of that compromise. Centralized logging and monitoring infrastructure costs money to build and staff, storage, tooling, and people to actually respond to alerts around the clock. So it's an easy budget line to shrink, especially at smaller organizations trying to keep costs down. Even where alerting exists, poorly tuned rules generate so many false positives, alerts for things that turn out to be perfectly normal, that teams experience alert fatigue and start ignoring notifications altogether, which defeats the purpose just as thoroughly as having no alerts at all. And because logging doesn't add a visible feature or stop an attack by itself, a customer never notices good logging the way they'd notice a new button in the app. It's frequently treated as a late-stage checklist item, something to configure once the product is already built and shipped, rather than a core part of the system's design from day one. Attackers benefit directly from poor visibility. The longer they can operate without detection, the more time they have to explore a network, escalate privileges, gaining access beyond whatever the first foothold gave them, and move from the first compromised system to more valuable ones nearby, a stage often called lateral movement. Without logging and alerting that flags this movement as it happens, an intrusion that could have been contained within hours instead continues for weeks or months, giving the attacker time to locate and exfiltrate the data they actually came for in the first place. The initial breach is often the smallest part of the damage. It's the undetected time afterward, sometimes called dwell time, that determines how bad the incident ultimately becomes. The fix starts with centralizing logs from every system into one place that an attacker compromising any single server can't easily reach or erase. On top of that centralized store, automated alerting rules should watch for known suspicious patterns, repeated failed logins, privilege escalation, unusual data access, and page a human in near real time rather than waiting to be discovered manually weeks later. None of that matters though without a tested incident response plan, a clear, practiced process for what happens the moment an alert fires, who gets notified, how the affected system gets isolated without tipping off the attacker prematurely, and how the investigation and recovery actually proceed step by step. Practiced here is the key word. A plan that's only ever been written down and never rehearsed tends to fall apart the first time it's actually needed. Let's bring it together. Security logging and alerting failures happen whenever a system can't detect or surface evidence that something has gone wrong. Missing logs for key security events, logs nobody actively monitors, or logs an attacker can tamper with to erase their own tracks. It persists because monitoring infrastructure costs money, alert fatigue makes teams tune out real warnings, and logging rarely feels urgent until the moment it desperately is, by which point months may have already passed. The fix is centralized, tamper-resistant logging that lives somewhere an attacker on one server can't reach. Real-time alerting on suspicious patterns instead of a static archive nobody reads, and a tested incident response plan ready before it's needed rather than improvised in the middle of a crisis. Next up in the series, the final risk, mishandling of exceptional conditions. What happens when a system's error paths themselves become the vulnerability? If you're prepping for a security interview, subscribe so you don't miss it. Part 10. Mishandling exceptional conditions. Type one unexpected character into a form and sometimes the system doesn't just fail, it explains itself. A full stack trace, an internal file path, the name of the database driver, sometimes even a fragment of a query, all displayed right there on the error page. That's mishandling of exceptional conditions. A system encounters an error, an edge case, something it didn't expect, and instead of failing safely, it fails in a way that helps whoever caused it. An exceptional condition just means anything that falls outside the normal path the code was written for. A value that turns out to be empty when the program assumed it wouldn't be. A network call that times out. A file that isn't where it was expected to be. Every program hits moments like this. What separates a secure system from a fragile one isn't whether it ever fails. It's what it does the instant that failure happens. This is one of the newer categories in the OWASP top 10, and it covers a simple but easy to underestimate idea. How your code behaves when things go wrong is itself a security decision, not just a reliability one. This category covers a few related failure patterns. First, verbose error messages that leak internal details, stack traces, file paths, library versions, anything that maps out the system for an attacker planning a next move. Second, unhandled exceptions that crash a whole service instead of failing just the one request that triggered them, turning a small isolated bug into a denial of service for every other user at the same time, because one bad request took the whole process down with it. And third, and often the most dangerous, error paths that accidentally skip a security check. If an authentication or authorization check throws an unexpected exception and the surrounding code isn't written carefully, the request can sometimes continue as if the check had passed. Not because anyone approved it, but because the failure wasn't handled at all. It was just skipped over on the way to whatever code runs next. These three patterns look different on the surface but share the same root cause. Nobody decided in advance what safe looks like when this particular thing goes wrong. When a security check, an authentication call, a permissions lookup, a signature verification throws an unexpected exception, the system has to decide what happens next. And that decision usually comes down to how the surrounding code was written, not a conscious policy anyone chose. Fail open means the default behavior on error is to allow the action anyway, which is convenient for uptime. The user's request still goes through even if something glitched, but it's dangerous because now any way of triggering that exception becomes a way of bypassing the check entirely. Fail secure, sometimes called fail closed, means the default on any error is to deny the action and stop, even if that means a legitimate user occasionally sees an error instead of getting through. It's the safer default almost everywhere a security decision is involved. An unexpected error should never be interpreted as implicit permission, because an error is, by definition, a moment where the system no longer knows for certain what's true. Handling errors correctly, for every function, in every language, is tedious, and under deadline pressure, it's tempting to write a broad catch-all block, a single line of code that says catch any exception at all, log it or ignore it, and keep going, which makes the immediate bug disappear from view without actually fixing what caused it or deciding whether continuing was even safe. Testing usually reinforces the problem. Most test suites are written to confirm the expected successful path works, log in with the right password, submit a valid form, not to throw malformed input, timeouts, and unexpected null values at every function to see what happens when something goes wrong. The result is code that's never once been forced to prove it fails safely, because nobody ever deliberately made it fail during development. So the first real proof comes whenever an attacker, or just bad luck, does it for them in production. Attackers deliberately feed a system malformed, oversized, or unexpected input specifically to trigger errors. Then read carefully what comes back. This is often one of the very first things done against an unfamiliar target, precisely because it's cheap and legal looking. It's just typing into a form. A verbose stack trace can reveal the framework, the database type, even internal folder structure, information that narrows down exactly which known vulnerabilities to try next, turning a blind guess into an informed, targeted attack. Worse, if they find a specific input that reliably causes a fail-open condition in an authentication or authorization check, that single crafted request becomes a repeatable bypass, a script or a saved request they can reuse at will, letting them walk straight past a control that looked solid under every normal condition anyone actually tested. The error path becomes the actual attack surface, even though nobody who built the system ever intended it to be one. The fix starts with the default. Any unexpected error in or around a security check should deny access, never grant it, fail secure, not fail open. Error messages shown to users should stay generic, something went wrong, with an incident reference, while the full technical detail, the stack trace, the internals, goes only into the internal logs. The same centralized monitored logs the previous video in this series covered, never into the response body itself. And error handling shouldn't be an afterthought. It should be deliberately tested, feeding functions malformed input, timeouts, and unexpected nulls on purpose, to confirm the system degrades safely instead of discovering the failure mode for the first time in production. A useful habit here is to ask, for every function that can fail, one question at design time. If this throws right now, does the system end up more open or more closed? If the honest answer is more open, that's the bug, even if nothing has exploited it yet. Let's bring it together. Mishandling of exceptional conditions happens whenever a system's response to an error, a crash, unexpected input, a failed check, ends up helping an attacker instead of stopping them. Verbose errors that leak internals, exceptions that crash a whole service, or worst of all, error paths that silently skip a security check and fail open instead of fail secure. It persists because error handling is genuinely tedious to get right everywhere, and because most testing only ever proves the happy path works, never that the failure paths are safe. The fix is to treat error handling as a security decision from the start. Fail secure by default, keep detailed errors internal and generic ones external, and test the edge cases on purpose, deliberately, before an attacker does it for you in production. That closes out this 10-part series on the OWASP Top 10 for 2025. From broken access control all the way through here, 10 different ways trust gets misplaced in a system, and 10 matching ways to place it more carefully instead. If this series helped you get ready for a security interview, or just sharpened how you think about building safer systems, subscribe, and thanks for following along.